Hi, this is Adam Griffin with the first video for this week. So this is going to be problem 29.11, which is a practice problem. So a little bit of info. They give us the magnetic field at the center of a 1.1 centimeter diameter loop is 3 milliteslas. So part A asks, what is the current in the loop? So the equation for the it says that the magnetic field at the center of the loop is 3 milliteslas. We know that, here, let me grab a pen really quick. There. So right here is 3 milliteslas. And we have the equation for the strength of the magnetic field at the center of a coil. So it's equal to our constant right here of 1.257 times 10 to the negative 6th Tesla meters per amp divided by 2 times the number of rotations, which is just 1 turn since it's just a ring and it's not actually a coil, times our current divided by the radius of the ring, So we know that our diameter is 1.1 centimeters because it says it up here. So our radius is 0.55 centimeters. We know that we want to find the current in the loop when the magnetic field at the center is equal to 3 milliteslas, or 3 times 10 to the negative 3 teslas. So if we plug in this for here, and then all of these 4 constants, so our U sub 0, our N, our B coil center, and then our R, we can find I. So we plug all those in, and then we can rearrange the equation. We get I equals 3 times 10 to the negative 3 teslas times 5.5 times 10 to the negative 3 meters times 2 times 1.257 times 10 to the negative 6 Tesla meters per amp to the negative 1. And that will give us 26.3 amps. So I wish now that I had written down this equation in variables and then plugged it in so you could kind of see how it's arranged, but all you really need to know is this equation up here. So I would say that the hardest part for part A is knowing that there's a difference between like the equation between the on-axis strength of the magnetic field from a coil. So like if you're a distance z out, there's a different equation for that. Whereas in the center, it's just based on the radius of the loop. So yeah, that's part A. I apologize if it's a little bit confusing. Hopefully everything is written down neatly enough. And then for part B, it asks, a long straight wire carries the same current as in part A, 26.3 amps. At what distance from the wire is the magnetic field 3 milliteslas? So here we have our figure right here. We know our current is 26.3 amps. We want to find this distance, and we know that the magnetic field is supposed to be 3 milliteslas. So for a wire, a straight wire, our magnetic field is equal to our constant, this constant right here, 1.257 times 10 to the negative 6th, divided by 2 pi times our current divided by the distance from the wire. So since our B sub wire equals 3 milliteslas, or 3 times 10 to the negative 3 teslas, we can plug that in. And again, I kind of did this in the same way as in part A, and I wish that I had rearranged it differently, but you can kind of just see where everything's going. So yeah, so we have our constant divided by 2 pi times 26.3 amps divided by our distance from the wire. So just through algebra, we can multiply both sides by r and divide both sides by this, and they basically just switch places. So our distance equals our constant divided by 2 pi times our current divided by our magnetic field strength. And that gives us a distance from the wire of 1.75 times 10 to the negative 3 meters. So yeah, that's how you do 29.11, which is the practice problem. I would again say that the hardest part of this is using the equation for an infinitely long wire instead of a wire segment. And yeah, just knowing how to rearrange them. But pretty straightforward, and I hope that I explained it well. But yeah, thank you for watching.